Okay, welcome friends to the last part of the lecture 3. So to continue, what we have been seeing so far is that there is this group called Lorenz Group, which is given by SO3 Now I'll briefly mention why this group is useful, essentially why we understand all this language. So with this we can classify all kinds of objects which transform under this group. So we can classify what are all the possible objects which can transform under this group. So these are called representations. So we'll keep using this word quite often. So if you have a group theory course later on in the next semester, you will have a chance to learn about these words in great detail. For us it doesn't really matter because we are going to say these things as objects which transform under various ways through Lorenz transformations. Lorenz transformations. So what does it mean? So suppose if we what we want to call is something, so an object which doesn't transform, say for example, which absolutely doesn't transform is the same in every frame of reference. Such objects are called scalars. Invariant under Lorenz transformations. That means in every frame of reference they carry the same value. So one of the things which we have seen already is speed of light. The second thing we have seen is ds square, the line element, is the same in every frame of reference. The line element is invariant under Lorenz transformations. So it is the same under every and under any frame transformation, in every frame is the same thing. Similarly, mass of, this is the rest mass of any particle. This I mean by rest mass. Okay, so the rest mass is the same, it's a scalar quantity, so it's a constant in the theory, like I am saying, like the speed of light or anything. The rest mass also is the same in every frame of reference. This constant, the speed of light, is sort of a special constant because it dictates the maximum speed one can write. Okay, but even the mass of a particle is also some sort of a constant, and it is a very important constant also. It sets some threshold at which these particles can be produced under relativistic annihilations of particle antiparticle essentially. So all the objects which carry no index, carry no Lorenz index, okay, are called scalars. So they are all invariant under Lorenz transformations. So they are the same in every frame of reference, which I have been saying, again repeating myself. So this is one point. Second kind of things which are called vectors. So these are objects which carry one index. So what are these objects? Say for example, x mu, we have seen one mu which is a 4 vector, which we have, say let's take the this metric CT x, y and z. Okay, so these have an index 1 because they carry one index with them. So these are called rank 1 index, rank 1 tensors or vectors. These are actually the 4 vectors because they transform together, and this way you can understand space time much better actually. Okay. What are the other objects? Like for example, there is a mu, which you can write it as a mu a bar. Okay, so minus sign here because you can take it, it's a contravariant. The covariant is not carrying any sign. Okay, so similarly, any object you can write down which has one index will be called as a rank 1 tensor or a vector. So we can actually introduce interesting quantities. We'll introduce some interesting scalars and some interesting vectors below. But to complete the discussion, the third class which are important actually is called tensors. Tensors are rank 2 objects. This we have seen no, in the vector potential. So vector potential of QED of electrodynamics. So the rank 2 objects which carry 2 Lorenz indices. So what are these things? So they can be, they are typically, because they are like they carry 2 Lorenz indices, you can think them as some matrices. So you must have seen this matrix in electrodynamics, F mu nu, F mu nu. So this is some field rank 2 tensor. This is also called field strength tensor. This has 2 indices. It turns out this is an antisymmetric tensor because it carries F mu nu is equal to minus F nu mu. Okay. So these are the kind of objects. Other one which you can think of is H mu nu, which is a symmetric tensor. And then the third one which you have seen is eta mu nu, which is just the metric tensor, which is also a metric tensor in GR. And so on. So there could be a lot of objects. This is also the field strength tensor, and this is related to our electrodynamics in this particular fashion, where del is the partial derivative. So these are the various objects which are called representations under which of Lorenz transformation. This is technically not the correct word because the particles what we all see are actually the representations of some other group called Poincare group, but I think this will be covered in QFT 1 course, which we won't go into with it. Poincare group, where x mu prime is equal to del lambda mu nu x nu plus a mu. So this is the transformations. So it has some sort of linear transformations also along with the ordinary. This is the Lorenz group and this is the linear transformation associated with it. Okay. Now let's given this set of representations or the various objects which transform under the Lorenz group. This is how they transform under the Lorenz group. So now let's look at some useful quantities, okay, which I'll introduce. So the first useful quantity I'll introduce is something called the proper time. So let's look at the scalars once again. Scalars. So the one which we have seen is something called ds square, that is nothing but minus t square. So let's just take one dimension for example. So this is nothing but to be make accurate minus dt square plus dx square plus dy square plus dz square. For 1D, this ds square is equal to minus dt square plus dx square. So this is called the line element. Okay. Now let me put the C also. So then putting the C, so ds square is actually minus c square dt square plus dx square. Define a line element, but not in terms of distance, but in terms of time distances, time elements, time periods. So these are time periods which are invariant in all reference frames. Instead of so you are looking at time periods which are invariant in all reference frames, and these are called proper time. Okay. So proper time is related to, that's it, is related to the line element by this particular case. So in the limit c is equal to 1 in natural units, ds square is equal to d tau square minus d tau square. So what we are trying to do is, we are trying to convert so we are looking at length intervals, right? Earlier we were writing the entire thing in terms of length, okay, which are invariant, length scales which are invariant under all transformations. Instead of length, we are looking at time periods which are invariant under all Lorenz transformations. These are called proper time. Okay. This proper time is an extremely useful concept. Okay. Which will be useful for defining certain vectors. So let's now look at various other possible vectors which we can define. So the other most important vector, if you want to study dynamics, is the velocity vector. Now in ordinary 3 dimensions, the vector is, which we know, which we define, is nothing but v bar so in 3D, 3 dimensions, v bar is equal to dr bar by dt. But this is not invariant in STR and special theory of relativity. This is not an invariant quantity, or it is not even a covariant form. So we won't write it everything. If you want to write it in for covariant one, we want to introduce something called 4 velocities. Vector. So this is defined as u mu is equal to dx mu by d tau. So where I used the proper time interval, so it is u mu is defined in terms of the proper time. Now you will immediately see that one implications of this vector, the fold velocity vector, is that u mu is equal to 1. From the above definition. One second, if I have 1 or minus 1, what did I do? I think I made a mistake in the definition. No, this should be c squared d squared, I think. Yeah. Okay, one of the implications of this is dx mu. Yeah, this is fine. Okay. I think I just cross check the notations. Okay. Okay, so now if you want to write it actually in terms of the four velocity, so expanding it, u mu is equal to gamma of v is the velocity, essentially gamma times c times v bar. Okay, this is the definition of four momentum. That is equal to c square, where c square is the definition of this one. Speed of light in natural units. This is what is in natural units. This is fine. Okay. Okay, now with this I can define something called the four momentum. Which is defined as p mu is equal to m times u times u. Now you have the famous relation p mu is equal to m square. Now p mu turns out is just e p bar. So with this we have minus e square plus p square is equal to m square. Okay, so this gives me the relation, but we can have the opposite direction also. Okay. So with this index you end up having this particular relation, which tells you that energy, momentum and mass. So even when m square is equal to 0, energy is non-zero, unlike in, so this is what happens for photons, unlike in classical mechanics. M square is by definition is always greater than 0, but if you have particles which have negative energy square, so m square is negative, say for example those are called tachyonic particles, which are unphysical. Now finally I'll introduce the last one, which is the last concept before going to the next lecture, which is the light cone. So if you have a particle of this particular type, so if you have a graph of this particular type, where let's take one dimension, on we have x on one axis and t on another axis. Now we can draw a line which is 45 degrees along the origin, where x is equal to t. So this is called this line is called the light cone line. Okay. So this sets the reason where minus dt square plus dx square is equal to 0, or ds square is equal to 0. So all the events which are happening on this line are called light-like events. Now if you have anything below, say for example this region, these events, okay, are called time-like. Okay. So in this cases ds square is negative, time-like events. Finally, you will have ds square positive, which are called space-like events. So in space-like events, what's happened? the space part is the dominant part, so ds square is positive. So why this is important? So the point is that we know that objects which most of the objects cannot go beyond the any object cannot go, especially if it's massive, it cannot go with speed beyond the speed of light. It's impossible to go beyond the speed of light as long as you believe in special theory of relativity and Lorenz transformations. So Lorenz transformations have an inbuilt quality that you cannot really so even if you go close, if you put in say something like 2c, if the velocity is 2c or something, they automatically cut off, meaning you cannot really go beyond you cannot increase the speed of a particle beyond beyond c. Okay, they have an inherent cutoff in it. So suppose if you cannot make successive Lorenz transformations, keep on making successive Lorenz transformations where you can go into a frame where the velocity of the light looks like it's more than c. Okay, so there is no way you can there is a okay. I'll spend it more detail on it on the next lecture, where I'll deal with these parts. So what's happening is that all the space like events are only possible, that means the interval between them has space separations which are larger than can be reached by any particle traveling with the speed of light. Okay, so these are events which cannot be reached, these are distances which cannot be reached by traveling with speed of light within the time interval. Okay, these are length scales which cannot be reached by light. Okay, whereas time like events or distances which can be reached even with massive particles, that means particles traveling even with smaller speeds than light. And light like events are essentially when your events which you cover which are moving with the speed of light. So most of the events which happen in time like zone happen sequentially in time. Say for example, so what I can do is I can call this as past, this I call it as present, and this I can call it as future. So if you sit here in this particular point, you can keep moving towards the future, whereas the past happens before you. You cannot have, so you can have sequentially timeline. So you can have only time ordered events, meaning there could not be, so you cannot say that okay, some event from future will affect things in the present, or some event, only the events in the past can affect in the present and the present events can affect in the future. So all these events are essentially causally connected. All events in the light cone time like region are causally connected. So which we call them as physical. So physically we are only interested in those events which are causally connected. Acausal events require space like separations which we are not interested. So you cannot really time order those events essentially. So they can be anything and they can move from here to meaning future can affect the present. Okay, those kind of things can happen. So this is the things which are important, and this is the kind of events which we will be interested in our course. So I will continue with special theory of relativity in lecture 4 also. Okay, so here I will stop my lecture 3.